give us a lecture. Professor Ko is a professor at the Seoul National University. He got his PhD from UC Berkeley in 2006. Then he did a postdoc at UC Berkeley till 2009. And he joined the CASE, the Korea Advanced Institute of Science and Technology, since 2009. Now he's a professor at the Seoul National University. His research interests include flexible stretchable electronics for wearable electronics and soft robot application, laser-assisted nano-material fabrication process development, laser nano-material interaction, and clock-assisted nano-manufacturing. Professor Ko is also an associate journal editor of the soft robotics. So Professor Ko will deliver a lecture on the transparent electronics with a stretchability, flexibility to us today. So let's welcome Professor Ko. Okay.
Thank you for your introduction. At first, I want to thank the Professor Jian for the invitation to this interesting seminar. So today I will present our research progress on the transparent electronics with the stretchability and the flexibility. Actually, I have been working on this topic over the past 20 years, and starting from the flexible electronics on the plastic and also the paper and fabric, and moved to the stretchable electronics, and currently working on the next generation electronics with the transparency and also the stretchability simultaneously. Firstly, I will briefly introduce my perspective on how the electronics technology will evolve in the near future. I have to say this is my very personal viewpoint, and then you may have a different perspective. And this may apply to any kind of electronics, but I want to give you an example of display. The first generation of the display started in a rigid and bulky shape. And usually this kind of a rigid and bulky display cannot be portable, but usually placed fixed on a shelf or to the wall. The second generation of the display is in a flexible form. And actually, we are in the transition from a rigid display to flexible display right now. The following generation of the display is currently under intense research development, are expected to be stretchable form and the transparent form too. Here, you may see that the next generation of display expected to evolve by adding the new value or new functionality from flexibility to stretchability and transparency and so on. So, and we may apply the same expectation for technology evolution step for all the electronics to change it from rigid to flexible, stretchable, and transparent form. Okay, so flexible electronics are the electronics built on the flexible substrates such as plastic, fabric, or paper, and it can be bendable and easily conform to the non-flat surface. And from the material such as plastic, fabric, and paper, you may expect that it will be light and durable than the conventional rigid electronics. And it is the best device form for the portable electronics because light and durable characteristics are the most important for the portable electronics. And stretchable electronics is built on stretchable or soft substrate, and it is an important device used for the human-friendly soft electronics or wearable electronics because human body is beyond flexible, but is more soft and stretchable. And one may think stretchable electronics is a simple variation of the flexible electronics. However, I think personally, I think stretchable electronics is very different from the flexible electronics and the way more complicated and difficult technology. And if the wearable electronics is made into a flexible electronics form, it will be better than rigid electronics, but it's going to be still uncomfortable compared with the stretchable and soft electronics. So the stretchable electronics will be an ultimate form of the wearable electronics, including the implantable electronics. And this stretchable soft electronics can be applied to robotics field, such as soft robotics. Okay, and compare with the flexible electronics and stretchable electronics. Stretchable electronics and transparent electronics has a relatively short history. And this is because there is a big technical hurdle to find the proper transparent conductor material. The new functionality that you may see the other side of the electronics will provide you extra information that has been missing so far. And the transparent electronics can be used for transparent display, smart window, or transparent solar cells for building integrated solar cell applications. Again, you may see that the next generation electronics is expected to evolve by adding new function, new value or new functionality from flexibility, stretchability, and transparency. And those technology evolution steps has been demonstrated separately. For example, flexible or stretchable electronics are not transparent so far, and transparent electronics are usually rigid and not flexible or stretchable so far. So in our lab, we try to combine those new functionality together. For example, we try to develop a transparent electronics that can be flexible or stretchable at the same time. So to realize the transparent electronics with flexibility or stretchability, what is the key issue and what is the possible technology? So that is going to be the first question. The key technology is definitely development of a transparent conductor. And as you already know, we have already a popular transparent conductor material, which is indium tin oxide, which is ITO. And most of the optoelectronics use the ITO as a transparent conductor. However, ITO is the worst material for flexible and stretchable electronics because it can be easily develop cracks and also break under material deformation and stretching. And for rigid electronics device that do not move at all, and ITO is a totally fine material, but we have to develop a new transparent conductor material that can be flexible or stretchable to realize the transparent electronics with the flexibility and stretchability. Actually, there are several candidates for this. And among them, in our lab, we usually use the metal nanowire percolation network. And metal is the very ideal material for electronics with the high electrical conductivity, but metal is usually non-transparent like this. However, if the metal is made into the nanomaterial, it can be transparent and while keeping the good electrical conductivity of metal. And besides the good electrical conductivity and transparency, and this can have good flexibility and stretchability too. And it is the ideal material to realize the transparent electronics with flexibility and the stretchability. And also there are two issues in realizing the stretchable conductor. So firstly, there is a material issue. And unfortunately, there are not many material that can be stretched and also highly electrically conductive as well. And some carbon-based nanomaterial, conducting polymer, liquid metal, and hydrogel can do this function, but there are still some problems in those materials. And in another way, highly conductive but unstretchable material can be made into stretchable form by making serpentine shape. However, this has also intrinsic limitation for stretchability. Besides the material issue, there is a manufacturing issue. And conventional electronics fabrication process usually use a high temperature process and also highly corrosive chemicals, which are not compatible with the flexible or stretchable materials. So there is a strong need for a new low temperature manufacturing process development. Here, we usually use the nanomaterial and the laser technology to develop this. So to achieve this goal, in our lab, we develop various technology from material to process and also the application. And again, to realize the wearable electronics, we develop the combination of the material development, processing scheme, and also the device fabrication. And they are basically three main components in engineering. However, there are not many labs who can do all of these three: material processing, material development, and processing development, and the device development at the same time. And most of the labs just focus only one or two items. And I think we are one of the few labs who can do all of these three items in the lab. And even though I'm in the mechanical engineering department right now, we develop material, and which will be pretty good. And some of the material or chemical engineering lab also sometimes ask for the material from our lab. And this is something I am very proud of myself. I am very proud of about my lab. And to realize the wearable electronics, basically we need to realize the four components in the flexible or stretchable form. The four components are firstly information display, and the second part is the information input device such as a keyboard or touch panel. And third one component is the information processing device such as a transistor and the memory. And the last component is the energy generation and storage device. These pictures are the demonstration of the in our lab by our lab student. Our graduate student are expected to go through the whole engineering cycle from material development and process, and also the final working device demonstration. And 20 years ago, our objective was to make all the electronics in the world into flexible electronics form. And then 10 years ago, it was changed to make all the electronics in the world in stretchable form. And right now, our objective is to make all the electronics into the transparent and flexible or stretchable form. To achieve this goal, we use the nanomaterial. And this is because nanomaterial has a very unique characteristics that is totally different from the bulk counterpart. And therefore, we may overcome the limitation of the conventional bulk material. And first characteristics of the nanomaterial we are interested in is the size-dependent thermodynamic property. And as we already know, material melting is a material property. And once we decide the material, it will be a fixed value. And however, if the size of the nanomaterial goes down to a very small size, melting temperature will drop as the size gets smaller and smaller. And for example, the melting temperature of the bulk gold is around 1000 degrees Celsius. But if the same material is made into the nanoparticle, and if the size gets smaller than the several tens of nanometer, the melting temperature can drop to almost like a plastic compatible very low temperature. So this unique thermodynamic characteristics may provide the potential for low temperature process development, because for flexible, stretchable, transparent electronics, because we are frequently deal with the low temperature materials. And second interesting characteristics of the nanomaterial is the size-dependent optical property. So for the same material, nanomaterial may show a totally different optical characteristics. For example, bulk gold usually show this kind of a yellowish color. However, when it is made into the nanoparticle, and it may show totally different color depending on the size. So if I don't tell you this is gold nanoparticle, nobody is going to recognize this is gold. So this happened due to the surface plasmon. And even though the metal itself is not transparent, and then it can be made into the nanowire, and it can become transparent too. So we can develop a transparent metal. And the last interesting characteristic in the nanomaterial is the size-dependent mechanical property. So when the system size gets smaller, the strength and the ductility of the nanomaterial will be increased compared with the bulk material. And for example, a single crystalline silicon is one of the most fragile material in the world. It is very hard to imagine to bend the silicon wafer into the 90-degree or 180-degree. However, this will be possible if the same material is made into the nanowire. So this picture shows that the silicon nanowire and then can bend almost like a 108-degree. So this enhanced mechanical property will play a very important role in developing the wearable electronics, which will undergo various mechanical deformation during the operation. So for a low temperature process development, we usually use the laser as a localized heat source to minimize the thermal damage to the substrate, and for several metal patterning without using the conventional photolithography and the vacuum deposition processes. So for metal patterning process development, the focus laser is irradiated on the metal nanoparticle ink coated on the polymer substrate. And then only the nanoparticle where the laser is irradiated will melt to make a continuous metal pattern. And the nanoparticle which was not irradiated with the laser, and it's going to be just washed away easily with the organic solvent cleaning. So this video clip shows the real-time metal patterning by selective laser induced melting of the nanoparticle for 4-inch wafer size sample. And this picture shows the final metal patterning on the various polymer substrate by selective laser processing. So because the process is very fast, almost like a 2 meters per second scanning speed, and it can be done in 5 minutes for 4-inch wafer size metal patterning. So compared with the conventional metal patterning by conventional photolithography and vacuum deposition process, and this is very fast metal patterning without using any vacuum environment. Because this is a fully digital process, there's no need for the photomask, and the design can be easily changed by just modifying the CAD data. The metal patterning resolution was decided by diffraction and also the thermal diffusion, and we could go down to several micron size when the continuous wave laser is used. And if we use the more fancy laser, such as femtosecond laser, and then we may minimize the thermal damage to the substrate and also the heat diffusion. So the resolution could be further reduced down to 200 or 300 nanometer. So this is almost comparable with the resolution with the E-beam lithography process, but this laser-based process does not need any vacuum environment. As a second processing method development to realize the highly stretchable and transparent conductor, we develop a new concept called mechanical percolation network. And when the metal thin film is pulled on both ends, and then it usually tends to generate the crack and then tear apart and finally lose the electrical conductivity. So additionally, the metal thin film is not transparent too. And however, when the metal nanowire percolation network is used for the electrode, it can achieve a high stretchability and also the high transparency at the same time. So compared with a traditional static percolation network transparent conductor, the mechanical percolation network can be highly stretchable while maintaining a good electrical conductivity and also the optical transparency. So we use this mechanical percolation network as a core platform to develop a stretchable and transparent electronics. So there are several parameters to make a highly conductive, stretchable, transparent electrode. Some researchers are trying to focus on the smaller development of a smaller diameter nanowire. So from our experience over past 15 years, what we found is that the smaller diameter nanowire may enhance the transparency only, while sacrificing the electrical and mechanical aspect. However, the longer nanowire can enhance the transparency and the electrical aspect and also the mechanical aspect simultaneously. So this is because the percolation network with the longer nanowire has a smaller number of the nanowire junction, and the number of the nanowire junction greatly influence all the mechanical, electrical, and optical properties. So we had better minimize the number of the nanowire junction, and usually longer nanowire can reduce the number of the junction, which makes all of the problems. So therefore, we try to develop a new synthesis method for long silver nanowire synthesis. Now, we did that almost 10 years ago or 15 years ago. And we could successfully synthesize ultra long silver nanowire over 500 micron lengths by successive multi-step growth. Because this is like a kind of like a longer than 10 years old result. I think there could be the better synthesis method, but at this time, this was kind of like a world record. And after synthesis, the silver nanowire percolation network usually need the thermodynamic at 250 degrees Celsius for several hours to reduce the junction resistance. However, this temperature is 250 degrees Celsius heating for several hours is relatively high enough to degrade the flexible or stretchable substrate material. So therefore, we try to develop a laser nano-welding process. And when the laser is irradiated on top of the crossing silver nanowire junction, and we could observe a very interesting phenomena of the laser intensity increase by 100 times only at the junction part. So the other part of the nanowire is going to be just at the room temperature. So this localized laser intensity increase is going to cause the local heating at the junction only, and induce the selective nanowire welding only at this junction part without the thermal damage to the substrate or thermal damage to this another part of the nanowire. And based on the very long silver nanowire synthesis and also the low temperature selective nano welding process, and we could make a first highly flexible and transparent conductor, which is even better than the graphene at the time when we developed this. And graphene had the world record for this transparent conductor. But for some part, our longer nanowire transparent conductor was even better than the graphene. So by adding another functional or nanomaterial to silver nanowire network, such as conducting polymer, and also very small amount of the carbon nanotube to the silver nanowire backbone network, then we could develop a highly transparent and also the highly stretchable conductor. And silver nanowire is kind of like a relatively expensive material because silver is not a cheap material. So as an alternative to silver, the copper nanowire can be used for the same purpose. Even though the copper is very cheap, 100 times cheaper than the silver, it has a serious drawback in the severe oxidation in the air. So during the conventional thermodynamic process, copper usually get oxidized and lose the electrical conductivity. So however, our laser nano-welding process is a very fast process, and it can finish the nano-welding of the copper nanowire before the copper nanowire get oxidized. So therefore, we could prepare the copper nanowire-based stretchable and transparent conductor without the oxidation problem. So furthermore, we developed a laser-based selective reduction to convert the copper oxide nanowire back to the copper nanowire, even though it's even after it's oxidized. So we call this nano recycling process, and this can be done several times repeatedly. So up to this slide, I introduced the material and also the processing method development. And from this slide, I will try to introduce the various example of the actual realization of the flexible stretchable electronics in a transparent form. And I think it's due to the time limit, I will go through this part kind of quickly. And if you are interested in the detailed technical information, and you may read the journal papers. So this slide again is a partial list of the application demonstration in our lab to realize the wearable electronics. So they are a mixture of the either flexible or stretchable form, and some of them are transparent and some of them are not transparent. So I will not introduce all of them, but in this presentation, I will mainly present the transparent electronics with the flexibility and the stretchability. So as a first example, we developed the various transparent and flexible electronics. And the first demonstration is a transparent and skin mountable flexible touch panel. And also we develop a flexible transparent memory by copper nanowire percolation network, and the transparent flexible UV sensor array of the selectively grown zinc oxide nanowire was also demonstrated on the flexible substrate. And the energy generation device such as a supercapacitor could be made into the highly stretchable and also the transparent form. And here we developed the cold shell type nanowire percolation network because the base silver nanowire has a poor electrical stability. So during the operation, the silver nanowire get disconnected pretty easily. So we introduced several inert materials such as gold or gold shell or polypyrrole layers to enhance the electrochemical stability. So you can see the real picture of the device, supercapacitor. It can be stretched a lot and around like 50%, and it's highly transparent like this. Efficiently to more efficiently capture the particulate matter, and it can be reused after a simple washing, and also the pressure drop is going to be very small compared with the PM capture efficiency. And also further, by applying the current to the filter, basically this is a metal nanowire percolation network. So if we supply the current, it's going to induce the Joule heating. So by just applying the current to the filter to induce the Joule heating, it can kill the bacteria and also the virus on the mask by heating, and while maintaining a moderate transparency to see the lip like this. So actually for this, we use the copper nanowire percolation network for this transparent mask, and also for the thermal sterilization. And electromagnetic interference shielding layer can be also made into the highly stretchable and also the transparent form. And this can be used to protect the delicate electronic device that can be sensitive to the environmental electromagnetic wave. And also if some device such as like a implantable sensor, which will be sensitive to the electromagnetic wave, and then because that kind of material device usually need the electromagnetic shielding material, which will be similar to the skin kind of property, stretchable and also flexible, and also it could be transparent too. And also the heater can also be made into the highly stretchable and also the transparent form. And the heater can be mounted on the skin. And for medical thermal treatment, so some treatment need the heating. And also the heater can be attached on the non-flat window, such as car windshield or ski goggle, to remove the frost formed on the glass substrate. And the heater can be patterned for the localized heating. So you may see that from with this infrared camera image, you can see that localized heating. But if you see with your eye, you cannot see any kind of pattern because it's transparent. But there is some kind of like a patterning of this conductive transparent conductor. And then when you apply the heat, and then only some part is going to be heated up, but you cannot see which part is going to be heated up because it's invisible to your eye. And the skin sensor can be also realized in a highly stretchable and transparent form, and by introducing the kirigami concept. And basically the kirigami is a Japanese style paper cutting skill. So by the combination of the mechanical percolation network of the metal nanowire and also the kirigami cutting, and then we could realize the highly stretchable and transparent sensors. So when we first demonstrated the transparent sensor, and the typical question was, why the sensor need to be transparent? So the answer was kind of simple. And this is because we can see the other side of the sensor, and then we can gain more functionality and also more information, which was basically lost when the sensor is not transparent. So the transparent sensor is expected to play a very important role when it is mounted on, especially on the face or directly on the wound. So in these days, sensor is not used, are usually used to monitor the biophysical signal from the skin for a long time. But if the non-transparent sensor are mounted on the face, or such as like some part of the face, and also the other exposed skin part, and it's not going to look good in a cosmetic manner. So especially when you use the sensor for a very long time. And additionally, if the sensors directly attached on the wound, and if the sensors are transparent, we may observe how the wound is going to be healing. So otherwise, like if the sensor is non-transparent, and if the sensor is directly attached on the wound part, and then actually you don't know how the wound is going to be healing. So the condition, you can gain more information directly. So the transparent and stretchable kirigami sensor were demonstrated to measure the EEG, which is the brain wave, and EOG, which is eye blinking, and ECG is a heartbeat, and EMG is a muscle movement. And so you may see that all of this data is real data, recorded data, image with the transparent kirigami sensors we fabricated. So as a practical demonstration of our transparent kirigami sensor, we try to use this transparent and stretchable sensor to control drone. And initially, we wanted to use the brainwave to control the drone. But as you already know, brainwave is kind of too weak. So finally, we used the EMG, which is a muscle signal, to control the drone. And with the selective laser induced Marangoni flow of the metal nanoparticle, we could demonstrate the 3D touch. And conventional 3D touch, such as a force touch in iPhone, usually use the 2 different layers, separate 2D location touch sensor and also the press sensor. So the 2 different layers just attached back to back. So otherwise, we need a special stylus, such as a Apple Pencil is going to be needed to get this kind of 3D touch functionality. So with the fine tuning of the laser parameter, we could successfully make a unique wavy pattern like this. And then the develop a transparent force touch could detect the touch location and also the touch pressure at the same time with just a single layer. So the sensing range is kind of broad and kind of sensitive too. And furthermore, with the help of the machine learning, and more delicate functional device could be provided to the transparent sensors. And to detect the hand motion, we usually need almost 15 to 20 strength sensors connected to each finger joint. So this kind of a sensor usually made into the glove shape, and then each of for the glove part, there are so many strength sensors embedded into it. So we develop a unique sensor that can detect the hand motion in a single sensor strip like this. So one sensor can detect the multi-degree of freedom hand gestures. So the AI or machine learning could successfully differentiate the superposed electrical signal from all the finger joint to this single sensors. So therefore, instead of using the glove type hand sensors with many strength sensors, we may use a simple single sensor attached on the wrist to monitor the hand motion. So this can be used for some kind of like a interface for a VR or the cyberspace kind of things. And the sensor could be more customized by adding a new function or erasing the unnecessary functions. So the sensor could be realized in a skin attachable, very thin sensors. And then this video clip shows that the arm detect we attached this flexible and stretchable transparent sensor on the human skin, and then we try to use that for the AR VR application. And besides the mechanical sensor, a highly sensitive transparent temperature sensor could be developed to measure the delicate temperature change of inhale or exhale to calculate the metabolic cost of the user. And this can be further used to endow the temperature sensing ability to the robot hand. Also, it can be made into this kind of array shape to measure the temperature distribution. So it could be transparent form and also non-transparent form, and could be a flexible or stretchable form too. And the transparent flexible heater can be used for transparent soft robot application. So from this slide, I'm going to change a little bit gear for this application part. So by attaching the 2 thin film layer with the different thermal expansion coefficient, a soft thin film actuator could be developed. And when it is heated up, and it's going to bend toward the film with the smaller thermal expansion coefficient. So here we introduce a transparent heater between the 2 transparent film as independent heat sources. And further, we introduce the chirality to introduce a more complex deformation. So for the same platform, it can bend like this, or with some chirality, or it can wrap around like this. So this was induced by the anisotropic thermal expansion coefficient. And then with the transparent anisotropic actuator, we could demonstrate a transparent soft crawling robot here. So we intentionally added the black mark at the edge of the crawling soft robot because this is transparent and then hard to observe the movement. So the transparent robot has a three different segment. So you can see that from this thermal image. Then the robot can move forward or turn left or turn right by just controlling which part is going to be heated up. And also additionally, we transparent Venus flytrap and also the transparent gripper could be demonstrated. So it's for a gripper, it's kind of hard to see. So there's a transparent gripper here. Then you can pick up this kind of material here. So when you heat it up, it deform and then pick up the target. And also we demonstrated various bio-inspired transparent or color changing soft robot. The first picture shows the transparent flapping butterfly. And when we tried to develop this butterfly 5 years ago, actually we did not know actually there is a transparent butterfly. So we made the transparent butterfly as a proof of concept of the transparent robot. But few months ago, I happened to find a very interesting picture of a very interesting similar transparent butterfly in nature. Actually, we did not expect this kind of butterfly really exist, but we just tried to make this out of our imagination. But actually there was a similar kind of a transparent butterfly. That was a kind of a pretty interesting finding. And also we may put the thermochromic ink on the transparent actuator. And also we could demonstrate the blossoming color changing flower. The flower is originally is black, but it can change its color to red when it blooms. And also both the color and the shape change when it is heated up. So here we also use the transparent heater. And in the similar way, by using the silver nanowire transparent heater, we could make a color changing chameleon robot on top of the multiple layers of the transparent heater with the thermochromic liquid crystal ink. So when it is off, you can see that it's kind of like a black color, but when it is turned on, and then you can see, and it shows this kind of various color with the different the patterns. It kind of tried to mimic the real chameleon skins. Okay, so this is the video clip of the chameleon robot, and this chameleon robot has several photo detectors at the belly to detect the background color where the chameleon is moving. And the color is controlled on the chameleon skin by heating the transparent heater with the thermochromic liquid crystal ink on it. The chameleon robot can make any kind of RGB color and some simple pattern for the chameleon camouflage in nature. So for this video clip, actually, we did not demonstrate the pattern shape, but the pattern shape also we can, by just patterning the transparent heater, and then we can also introduce the pattern color, different colors. And the transparency is kind of a relative term. So for human eye, and the visible wavelengths will be detected by eyes. But however, another insect can see another wavelength, such as a UV or IR, and that can not be detected by human eyes. So in the military purpose, the invisibility in both UV and also visible and also the IR infrared wavelengths is very important. And we try to develop a thermoelectric based camouflage skin in infrared and also the visible wavelengths. So it's the thermoelectric material can cool down or heat up by just controlling the current. And also it can be made into this kind of a matrix shape. So we can control each of these thermoelectric modules and to control the temperature. And this temperature is going to be reflected back to this color because we usually use the thermochromic ink on top of it. So depending on the temperature, the same pixel can show this kind of blue color or green color or red color like this. And also this can be demonstrated for infrared range. So this is the mounted devices. And then you can see that this is basically the infrared camera image. So the black color means it's a low temperature part and bright part is the high temperature part. So when it is moving and then when it's mounted on the skin, then you can see that it can be cooled down, and then it shows a pretty similar infrared kind of characteristics with the background. So it's going to look like this part is empty. So when it moves to the high temperature part, and then it can change the infrared characteristics again. Also, it can adapt to this background infrared temperature. So it's going to also look like an empty part. So if we can scale up this kind of infrared and visible wavelengths skin to like a human size, and then we can induce the thermal camouflage to the bigger scale. So when this infrared and visible camouflage skin is mounted on the skin of a soldier, and the camouflage in visible wavelengths, so it can mimic this kind of a color and the pattern on the soldier uniform, and also it can be camouflage the infrared heat signature of the human body. Actually, this idea was obtained from the old movie, which the title is Predator, and it's starred by Arnold Schwarzenegger. So I think it's whether you have ever seen this one. This one is very interesting and exciting movie. So if you have any chance, I suggest you to watch this. So you can see here, Arnold Schwarzenegger is almost dead, and this alien can see only infrared wavelength range. Then the Arnold Schwarzenegger happened to covered with the mud, and his signature was blocked. So even though Arnold Schwarzenegger was just in front of this alien, and the alien could not see. So if we can control the heat signature on the human skin, and then we can do the very similar thing. And then you may have some question why we need to just focus on this heat signature, because currently in the military, usually they do not use the visible detection. So the covert operation usually done in the on the dark. So infrared detection is very important. So if we can hide our heat signature, then we can make a very important infrared camouflage devices. So we are trying to use this kind of technology for the this kind of camouflage things, and this can be used for the military, not just for military, and this can be used for the leisure and so on, and also the fashion things. So let me summarize my talk. And in our lab, we have been trying to develop various electronics in flexible or stretchable form to realize the wearable electronics. And in recent years, we are trying to develop a next generation transparent electronics with the flexibility or stretchability. So the reason why we focus on the flexibility and stretchability, because we want to use them for wearable electronics application. And because the human body is not just a rigid, it's somewhat soft and stretchable too. So for a better compatibility, all of the electronics should be made into the flexible or stretchable form. And we have demonstrated many devices in from information display and information input and information processing, and also the energy devices. And we hope to integrate those developed components to realize the fully functional wearable device in the near future. Okay, so that's it for my talk, and thank you for your attention.
Okay, thank you very much for your very interesting lecture. You tell us so many wonderful results on the material synthesis, material processing, and the application. Actually, in the application part, you mentioned so many different devices. Yeah, it's really amazing. Okay, so now it's open for question and comment. Any question or comment? Or maybe I can ask the first question. So for the material part, for the materials processing part, you talk about one is you put a polypyrrole on some metal nanowire. As you told us, it can improve the stability. So how much is the improvement in the stability?
Oh, actually, if you do not have any coating layer, shell layer, during the electrochemical study, it's gonna look like this. Everything is going to be just disconnected. So just one scan is gonna kill the sample. So it's gonna give a very big difference. It's a simple coating, and if we do not have any coating, and then the stability of this silver nanowire is going to be very unstable.
I see. Okay. Thank you.
I have one question.
Please, yeah.
Oh yeah. Professor Ho is very okay. Nice talk. Okay, I learned a lot. Okay, but most of I cannot get the principles. I need to learn more. Okay, so one question is when you control the figure movement, right, through some attached to the wrist, right? What the principles? Yeah.
You mean the machine learning sensor, right?
Yeah.
Oh, this one, right?
Yeah. You control the finger, right, through some skin electrons on the wrist, right?
Yeah. So basically, this is a resistive sensor. So when the finger is moving, and we call this part as a epicentric motion part. So all of the this finger connected muscle should go through this part. So when this the finger is moving, and then we can see the very slight muscle movement here. And then depending on the location, even though there's only single resistive sensor here, and then all the sensing data is going to be kind of like integrated. So we can have only one single signal. Then this one single signal actually contains the inference from each of these fingers. But if you just see that, and actually you cannot see the difference, but by just using the machine learning, and then machine learning can differentiate whether the signal came from this finger or this finger or this finger.
Okay.
So
okay.
That actually, without the machine learning, we cannot do this kind of function.
Okay, so in that case, for different people, maybe the signal will be different, right? So you have
But if we also use the transport learning, so another people use this kind of thing because after the learning, and then we can do the very short calibration, like just 3 seconds or 5 seconds, and by using the transport learning, and then we can directly use the learning data to another people pretty easily. So this called as transport learning here.
Okay, so you have a test this you call it epicentral a muscle movement, right?
Yeah.
Okay. Oh, so that's very nice. Okay. I read down your paper. I will read carefully.
Yeah.
Very nice. So, okay.
Physically.
One more question. Sorry. Okay. One more question.
No,
I can you have done a lot of application using the so for some movement, right? You use a the nature inspired. Okay, this movement, the motion, right? Yeah. So for that one, so how do you control that one? Okay, it's through the thermal, right? Thermal energy. Oh.
Yeah. Actually, because my background is thermal science, so we usually use a thermal, heat control to induce the, for the color change and also the movement, deformation, for everything, we usually use the heat.
Okay.
So most of the part I showed you in this picture, and then without the sensor, because sensor does not change anything. So besides the sensor, color change thing and the shape change thing and actuator, everything, most of the part is just we usually use the heat.
Okay. Very nice. Yeah, it's very nice. Okay, thank you. Okay, maybe I read more paper.
Okay.
Group. I can learn more. Yeah. Okay. Thank you. Yeah, very nice talk.
Thank you very much. Yeah.
Okay, Professor Ko, let me just continue Professor Chin's question.
Okay.
Just now he asked for the movement, you use the heat to control it. So may I ask what is the temperature?
For this one, you may see that. So we try to induce the deformation at the relatively low temperature. So you can see that it's around 50 degrees Celsius, but conventional actuator usually is a pretty high temperature, like around over 100 degrees Celsius. But our device is kind of pretty efficient because everything is built in. So we could induce this kind of deformation at the relatively low temperature. So it can be done around 50 degrees Celsius or 40 degrees Celsius.
Oh, that's not high yet.
Yeah, but it's still high, but it's compared with another electrothermal actuator, it's kind of low, I think.
Yeah. Okay. Any more questions? Yeah, I think certainly we need more time to digest your lecture. Yeah, we will read your papers here. So, Professor Chin, do you have any other comments or we?
Yeah, I found a very nice talk because I need some time to catch up.
Okay.
Yeah.
I should have
too many
more.
information come to my mind. Come to my too fast.
Yeah. Maybe after the COVID-19, we can invite you to Singapore. So that will be easier for us to understand the knowledge.
For long time discussion, I think maybe you are too busy enough here. Yeah.
I usually visit Singapore almost every year before COVID-19, but I haven't visited Singapore for a long time.
No, I think between Korea and Singapore is already open, right?
Yeah, that's right.
Yeah.
But still, when we come back to Korea, we have 10 days, self quarantine.
Still in Korea, still there's
we still have, but I heard that it's going to be removed, but we still have.
Yeah.
Oh, okay. In Singapore, if you have have the vaccination, right? Inject 3, have the booster. Okay, no need. Even no need to the PCR, ART, measurement, no need.
Yeah. That's much better. As you know, like currently in Korea, we have so many